Hello, my dear students, and welcome again to a new chapter with this course, Selected Topics in Electronics Engineering. Actually, I believe that you can understand that due to the nature of this course, we are going to go through various, maybe to some extent, unrelated topics related to advanced electronics. However, maybe we agree from day one that our common ground will be to investigate what is inside a sensor, typically an IoT sensor. And we started together with the first maybe 3 to 4 chapters or lectures in this course with the title of Interfacing Circuits for Sensors, where we consider first standard environmental sensor. We take an example for an CMOS based temperature sensor. Then we go to some sort of a biosensing techniques using first FETs, field effector transistors, typically OFETs, organic field effect transistor, and also we demonstrated the results for the schematics for the piezo-based sensing. Typically, we use piezo-capacitive interfacing circuit for blood pressure. I think we have an example, and we solve together an example for that. Maybe today we are going to go through relatively different topic, but still under the IoT nodes or IoT sensing nodes interest. From the first impression, you will believe that we are far from sensors, but by the end of the day, I will try to prove you that we are still inside the sensor node. So our topic today is related to parasitic capacitance. I think we already have demonstrated this point somehow in chapter or lecture 2 when we consider the FET-based biosensing techniques, where we highlighted the impact of the parasitic capacitance in field effect transistors. I think we have an example with the non-MOSFET, and we also solve another example during the tutorial. We solve another example with the thin film transistors or the TFTs. But today we are going to consider it from another point of view. One of the very important and essential blocks in any sort of a biosensor node is what we can call a transceiver. In a transceiver, basically a transceiver is a transmitter and a receiver circuit. And once you go to a receiver circuit, I think based on your communication background, you can understand that filters are a basic block in any receiver. Maybe in your electronics 3, we have to demonstrate together some sort of filters. And one of the very famous filters is what we can call the RLC filter. So what is an RLC filter? Let's try to go to the whiteboard and see together how the RLC filters work. So generally speaking, when we have an RLC filter, we have something like that. So we have a coil, an inductor, a capacitor, and then a resistance. That we call it an RLC or RLC filter. Okay. So if we go to the frequency analysis of this filter, my dear students, you will recognize that the frequency analysis for this filter is very straightforward. I think if you already used to listen to my classes in electronics 3, for example, you will remember that when we have this parallel combination, usually we go to the admittance Y, and we say that the admittance Y is simply 1 over SL plus SC plus 1 over R. So you can simply here use this admittance to get the overall equivalent impedance of this circuit. So the Z parameter or the Z the impedance will be 1 over SL plus SC plus 1 over R. This is the equivalent Z for this circuit, and then you can make this basic mathematical adjustments in order to make it in a second order filter, where you will find that this filter has, sorry, this filter, yes, okay, let's make this, okay, so we will find that this filter has two poles, so it will end up with something like that. This will be the output of a band pass filter. So let's go back here to the slides. Okay, so this will show this high frequency response for our RLC filter. So how we can manage this, or what is the correlation between this filter and what our topic, and what about the wood amplifier? We call this as a tuned amplifier. So basically, this is a passive version for a bandpass filter. What I mean by passive version is this is simply, it's not a gaining unit. It's not going to make any sort of amplification for the circuit or for the signal. It will filter the signal based on the cutoff frequencies, the high and the low cutoff frequencies. So it will basically filter the signal based on that. Without any amplification, as I mentioned. However, when we go to a tuned amplifier, then we are seeking not only to make a filter, but also to make a tuned, some sort of amplification performance. One of the very famous circuits that can perform this task is a very simple circuit. So I think that all of you have already worked with the MOSFET as an amplifier. I think most of you see before this circuit where we have a MOSFET. Let's say, for example, we have an n channel MOSFET, and then we have this resistance for a biasing condition. And here we have a coupling capacitor, and then we have the input. And on the other hand, we have some sort of a resistance here. Usually we call it RD, if you remember, and this is the output, the output. Sometimes we can have a source resistance here or not. It can differ from one amplifier to another, but this is a very commonly used, we call it a common source configuration for a MOSFET. So we have a capacitor. This is a coupling capacitor to get rid of the DC, and then the gate is DC biased by this potential divider, and then we have a load. And this is the output. And I'm sure that all of you have already solved a lot of problems in electronics 1, 2, maybe in 3, but mostly in 1 and 2, you solve a lot of problems where we have this common source configuration for a transistor. But now the question is, this is a very directly amplifier, but what we are searching for is that we are searching for both. We are searching for an amplifier and a filter. So what if we turn this load, this RD, not only to be in this format, but also to be like this? So your output now is not only a resistive load, it becomes in a form of what we can call in a form of what we can call a complex impedance format, where we have R, L, and C. In this case, if you go deeply to this circuit, you will find that you have two main functions. First, this gate-drain relationship, in terms of, if you remember GM, the transconductance of a MOSFET, will enable you to perform some sort of a gain for your signal. But this gain will be only considered to this filtered signal. Here we have what we can call a resonance effect. Typically, the meaning of a resonance effect is a certain frequency at which the impact of the capacitance is cancelled by the impact of the inductance. Simply, it's a very simple relation. We have here SL and we have here 1 over SC. So this is SL. So you can simply search for a value at which the impact of SL is cancelled by the impact of 1 over SC. At this value, your circuit will return back to be a purely resistive load with a maximum gain. This will be your resonance frequency. Otherwise, the response will be decaying response, making such an resonance bandpass filter. And again, you still have this gaining factor due to the MOSFET configuration. And this is one of the typical examples to make an standard tuned amplifier. So back to slides. Here is what we can call, my dear students, the AC analysis for the circuit, because all of you know is that whenever we start making an AC analysis, we deactivate all the we deactivate all the DC supplies. So back to the presentation. So back to the slide, to the whiteboard here. This VDD will be deactivated, making all these terms to be grounded. Later on, we will see how we can get rid of this using what we can call the radio frequency choke. We will describe it later on, but let's assume that we don't have these two resistance late now. So simply we have a drain connection or a drain node connecting our L and C directly to the ground, because this is a deactivated node. So as you can see, back to the slides. As you can see, this is simply the circuit where we are searching for. Sorry. Okay, so this is the circuit we are searching for. And using the very standard small circuit model for a MOSFET, you can solve this circuit in an easy manner. So this is simply GM-VGS, which is simply GM-V input, because V input is VGS. No current is flowing in the gates. That's why we have this open circuit. And then these are the resistance, the capacitor, and the inductor of your circuit. And using this, it's very straightforward that the voltage drop here, which is the V out, is simply the current flowing here in this voltage dependent current source flowing in these three elements. So the equivalent, the impedance equivalent. So this is simply, if you remember, this is the impedance. So GM times V input over this impedance equivalent, then you get what's V out, and or you can get the gain as a V output over V input in this format. So this is simply a tuned amplifier, or a very basic circuit for a tuned amplifier. As you can see, in one hand, this is a gaining factor. It's a gaining circuit because you can control this value GM and the value of the R, so that when you have the output over V input is, you have some sort of an amplification. So this amplification exists, and you still have this S domain function making you having this filter effect in order to make a second order filter. This is a circuit, and this is the frequency response as I just described. When you have a resonance here, the point of resonance is simply the point at which the frequency or the impact of the inductance is cancelled by the impact of the capacitance, making your circuit as a purely resistive circuit. And here there are three main parameters where we can demonstrate here. First is what we can call the resonance frequency, which is a very straightforward, actually. It's simply the frequency at which the capacitance is cancelled by the inductance. So simply SL equal 1 over SC, replacing S by J omega. So it's omega square equal 1 over LC, or omega equal 1 over root LC. So this is the resonance frequency at which you don't have the effect of the capacitance and the inductance. The second is what we can call the bandwidth of your circuit, which, or sorry, of your filter, which is simply defined here by 1 over CR. And as I just mentioned, at resonance, you don't have a capacitance and inductance effect. So simply the gain will become GMR. This is the gain you are going to face at the point of resonance. Herein also we are describing a very important factor. I think you already know basically the concept of the Q, or the Q factor, which represents the sharpness of your filter by dividing the resonance frequency over the bandwidth. So the lower the bandwidth, the higher the sharpness of your frequency response. And generally, this is a general gain that you have in all cases. So this is a very basic circuit that describes how you can make a tuned amplifier. Maybe we can have a very straightforward example here when you see this circuit. For example, it's required to design a tuned amplifier where let me close the camera. Okay, tuned amplifier where shown in the figure below, having give me the frequency is 1 megahertz, and the 3 dB bandwidth is 10 kilohertz, and the central frequency gain is negative 10 volt over volt. The fit available has at the base GM equal 5 milliampere per volt, and our output of 10 kilo ohm. The output capacitance is the output capacitance is neglectedly small. Determine the value for RLC. Maybe there is one added parameter here, which is R node. I believe that most of you already have discussed before the R node value. The value or the impact of the R node can be seen here. Let me show it to you using annotations. So this R node value will be added here as a resistance here. So by the end of the day, now your resistance is not only RE or sorry, RL, it will be RL parallel to R node. That's simply the main difference between the example we studied before and this example. We have the impact of R node. If you remember, R node is the output resistance for the MOSFET, and this is usually considered whenever you have a realistic MOSFET model, mostly in the ideal MOSFETs, we assume R node equals to infinity, but in real measurements, we usually have this small slope appears in the saturation region that can be expressed as in terms of R node. But let's go back now to the concept itself. So this is the R node. Now we can start designing. So simply we have the gain, we have the center frequency gain, which is negative 10. And back to the previous slide, you will find that yeah. Sorry, what? Okay, yeah. So the gain is GM times R, but take care, my dear students, that now R is equals to the equivalent between RL and R node. So we have GM. GM is given with GM is given with 5. We have the gain, which is negative 10, which simply means that the R equivalent is equals to 10 over 5, which is 2. We have already one of these two R's, which is 10K. So we are just searching for the other R, which is RL. So you can simply calculate RL from this equation, knowing that you already have the R node. So R node parallel with RL equals to 2 kilo ohm, and then you can make it very straightforward. Then if we turn back to the bandwidth, we will find that the bandwidth is 10 kilohertz, and we already know that the bandwidth is 1 over CR. So you know now R, again, R is the equivalent resistance, RL times R node, which is 2 kilo ohm. And we have the bandwidth, which is 10 kilohertz. So simply C equals 1 over BR. R is 2 kilo ohm, and B now is 10 kilohertz, which turns to 20 kilo and kilo will turns to mega in the denominator, which is micro in the in the denominator. So it is 1/20 macro farad. This is the capacitance. And finally, we have the band where we have the resonance frequency, which is 1 megahertz. You already calculated the C, the capacitance, so you can simply calculate the inductance value, knowing that the resonance frequency is 1 megahertz. So it's a very straightforward design problem for a tuned amplifier. But the question is, what about this word? The output capacitance is neglectably small. What is the output capacitance? And when we can neglect this output capacitance or not? This is mainly the topic of our lecture today, which is the parasitic capacitance effect in such an RF design. So we already have observed together this slide maybe 2 lectures ago, when we studied the field effect transistors in general for biosensing. And I have already highlighted for you the impact of the capacitance, where we demonstrated different capacitance impacts. Maybe the model you're having now is, we call it a solid state and capacitance model. So we are exploring the capacitance model in terms of a subtransistor level. Exploring, for example, we have an oxide layer here, which will create by default a capacitance. We have a depletion capacitance due to the channel. We have an overlapping capacitance due to the overlapping between the gate oxide and the source and the drain and so on. But to make life a bit easier, when we go to transistor level, we can express it in terms of a terminal capacitance. So simply we can say that between each 2 terminal, we have some sort of a parasitic capacitance in the MOSFET. For example, let me give you an example for that. Here we have, this is a gate terminal and this is a source terminal. And as we previously discussed, there is an overlapping area between this oxide and the source, making this orange capacitance, if you remember. 2 lectures ago, we already demonstrated. So simply, this is a capacitance connecting the gate to the source. So we can call it here, as you can see, CGS, or the capacitance controlling gate to the source, and so on. You can make another one between the gate and the gate and the drain, and finally another one between the gate and the source. So this is how we can rearrange, let me say, how we can rearrange the capacitance to be in terms of nodes on a transistor level, rather than to be in terms of the MOSFET schematic in a solid state subtransistor level. But again, how can these capacitors impact us in our design? This is a typical example for one of the models for a standard MOSFET, where they show a capacitance in the picofarad range, ranging from 1000 picofarad, which is 1 nanofarad, and going down again with the variation of the VDS, because basically the capacitance impact will change or will vary by varying the biasing condition. But generally, we are considering a picofarad range capacitance, maybe from sub hundreds, tens of picofarad, up to maybe 1 nanofarad. Again, here we can see the 3 capacitance of interest, as you can see. But maybe this is some sort of a semiconductor solid state topic to investigate such graphs. But now we are considering this from a transistor point of view, from a circuit's point of view. How can this impact us? Actually, this has a significant impact to our design. From one hand, if you return back to this slide or to this schematic, and now let's try to think about, what if we have a drain source capacitance? A drain source capacitance, simply it means that we have a capacitance here connecting the drain terminal to the ground, because simply the source is ground. So we have a capacitance here, which is in parallel to our CL. this is typically mean that the overall capacitance value will change. Generally, you have, so this parasitic resistance, as I just mentioned, the resistance between the drain and the source will appear here as an added resistance to the system. So we can draw it here like that, for example. So that's mean basically you are going to change the equivalent resistance of your circuit. Instead of having only CL, you will have CL parallel to the C, or C parasitic. Let's call it CP, for example, or CDS or whatever. But actually, this is not the only impact of the parasitic resistance to your system. There is also a very major impact in the small circuit model of a MOSFET, which we call it the parasitic impact. The parasitic impact occurs occurs due to the CGD, or the gate drain capacitance. Because simply, if you return to the standard small circuit model for a MOSFET, you will find that we usually have this open circuit disconnecting the gate side to the drain side. However, with applying the parasitic capacitance impact on your circuit, then you should start to have this CGD impact, or gate drain impact. This is a very major impact or effect for the parasitic capacitance, because simply this capacitance is feedbacking the output to the input, making this a connection that could be considered. So what you are going to do simply, my students, is you are going to add 3 new capacitance. So CG is a CDS, which simply impacted the overall capacitance of your filter. So CGS, we can consider this with a minimum impact to the system. And the CGD, which connects the output to the input, making this significantly important. Later on, we are going to discuss in detail how you can analyze this Muller effect on your circuit or on your amplifier. We will make a detailed mathematical description for that, but let's keep this on mind. Another important or another topology where we can implement our tuned amplifier is not only using MOSFETs, but we can also implement our amplifiers using bipolar junction transistor. And this is one of the very famous topologies used in a lot of transceivers, radio and RF transceivers, where you use a standard bipolar junction transistor in order to make your amplifier. Again, this is quite similar to the MOSFET topology. Here we have a common emitter topology. The input is inputted to the base. The output is taken to the collector. We have a common source. Usually we know that we have some sort of a bypassing capacitor. As you can see, this one and this one, these are bypassing capacitor cascading systems just to get rid of any DC offsets. Then we have this double filter effect. So this is simply the input. Then you have an LC filter, which is a band stop filter to make sure that you are getting rid of any undesired or unneeded noise from your circuit. Then you pass through this bypassing capacitor, going into these 2 resistors, which are very commonly resistance used to make the sufficient bias to the base. Herein we add this RFC, or what we can call radio frequency shock. What is radio frequency shock? The idea is very simple, my dear students. You need these circuits or you need this branch to be considered in a DC analysis. As all of you know, our conductors, our coils, are considered as a short circuit while considering a DC, J omega L, where omega tends to 0 at DC. So while we are doing your your DC analysis, I'm sorry, while you are doing your DC analysis, these coils will be directly considered as a short circuit, making the sufficient DC biasing to the base point through a potential divider between RB1 and RB2. However, once your frequency gets higher to the AC frequency needed, you can adjust your coil value so that this J omega L tends to a relatively high value as at the desired frequency. So once this J omega L tends to be high, tends to infinity, for example, or theoretically, this coil turns to be considered as an open circuit, making no effect for this RB1 and RB2. And since this is simply how you can control your biasing branch to be considered in the DC analysis and to be shocked in the AC analysis, that's why we call it radio frequency shock. It's whenever you are at the desired radio frequency, you shock this branch and get it out of the circuit by considering this J omega L very high. And then, still applying the same concept, we have here an amplification concept between the base and the collector. And again, you have your RLC load to be connected to the collector, typically as we did for our MOSFET circuit. But again, as we have a parasitic capacitance in the case of MOSFETs, we still also have a parasitic capacitance in the case of BJT or bipolar junction transistor. Let's try to flashback this. A bipolar junction transistor generally is an NBN junction. That means that you have a PN junction connecting the base to the emitter and another PN junction connecting the collector to the emitter. In the active mode, if you remember, my dear students, in the active mode, we are acting toward having the base emitter junction to be forward. This is simply happened by DC biasing this base terminal to be 0.7, making this base emitter junction to be forward. Alternatively, we act to have the base collector terminal to be reversed. And following our semiconductor concepts, we know that when you make a PN junction in a reverse bias, that means you are increasing the depletion region, which is between quotation, a non-conducting or an isolated region. Once you start to have a depletion region, increasing depletion region, means typically you have a capacitance. And again, this capacitance is connecting your input to your output, which is typically as the CGD capacitance you see in a MOSFET. So again, it has the same what we can call Miller effect. So before going into solutions, how can we get rid or reduce or eliminate this Miller effect, either in a PGT or a MOSFET? Let's try to think about how we can analyze this circuit, because basically it's very tough mathematically or circuit-wise to analyze this input-output model where there is a capacitance connecting the output to the input. So in order to make life easy, there is some sort of a mathematical or maybe a circuit tricks that you can use in order to analyze your circuit in an easy manner. So let's see now one of these tricks where you can analyze your circuit or analyze your small circuit model with considering the Miller capacitance. So generally, either you have a bipolar junction transistor or a MOSFET. In both cases, we know that we are considering this as an amplifier. So I can generally model either the MOSFET or the BGT as an amplifier. With an input and an out. Okay. The problem is, due to this impact, due to this Miller effect, a capacitance is appear to feedback the output to the input, which let's call this ZC, where ZC is the equivalent impedance for this capacitance. So it can be 1 over J omega CDG or GD in case of MOSFET, or it can be 1 over J omega CP or collector base in case of BGT. And as you definitely recognize, this makes your small circuit model very, very challenging in terms of analysis. So what you can do, my dear students, is you can go to make what we can call the equivalent impact of the resistance of the impedance. How we can make it? So this is the input, and this is the output. How we can make this equivalent impact? Let's consider it first from the input side. As you can see, my dear students, here, no current is flowing into the operational amplifier because simply let's consider it as an ideal operational amplifier. So no current is flowing here. So the current is mainly flowing in the ZC. The current flowing in the ZC, which is typically I input, is equals to V input minus V output over ZC. So I input, let's write in this side, it's more clear. I input equals V input minus V output over ZC. And as you know, A, which is the gain of the system, is V output over V input. So I can simply replace this V output by AV input, making I input equal V input minus AV input over ZC. Or we can say that ZCI input equals V input times 1 minus A. Okay, then what about Z input? So Z input is V input over I input, which will be ZC over 1 minus A. So if you have a Miller capacitance connecting your output terminal to the input terminal, this Miller capacitance can be considered as a input impedance within value ZC over 1 minus A. As you can see here. In the same manner, my dear students, we can redo this in a form of an output equivalent circuit. So again, considering that we have, let's do it here. We have an amplifier. So this is the input, this is the output. This is the ground again. And we have the ZC appears in the output side. Let's now consider Z output. Okay, so Z output is simply what? Z output is equals to the output is simply Z input times the gain unit A. So Z output is A ZC over 1 minus A, which is simply the same value we consider just with multiplying by A in the output side. So this is basically the procedure of how you can analyze this capacitance. So back to our presentation slides. So when you have this CGD, you can simply go to your standard small circuit model, which is this one. And then the CGD here, let me use the annotation again. So this CGD will going to be divided into two capacitors. One will appear here in parallel to CGS, and another will appear here. And again here with respect to our RF tuned amplifier design, we will be more concerned toward the capacitance appearing between the drain and the source, because this will impact again the overall capacitance of our RLC filter in the drain side. Similarly applied when we go back to this. Yeah, let's do it here. When we go back to this structure in the BGT, again, the same will happen, that we are going to split this base collector capacitance into two capacitance, one in the drain side, and sorry, one in the collector side and one in the base side. And again, the one in the collector side is much more important because this will impact the overall capacitance of your RLC filter. But back to the question is how we can get rid of this impact or of this effect, because as you can see, such a parasitic resistance will act to change our resonance frequency. So simply, if we go to this circuit again, where we consider a resonance frequency as 1 over LC, now your C is not C. Your C is C parallel to CDS parallel to the equivalent of CGD in the drain side, which can change the value of the C. So here we have mainly two ways to go through. First, does the value of this parasitic resistance really affect our circuit? Or in other words, does this parasitic resistance lie in the same range, in the same order of magnitude with respect to our circuit? So, as we see in this slide, for example, for this MOS, here the resistance is mainly in the pico, let's say nano, sub 10 nano, or a few nano farad range. So if your capacitance, if your circuit capacitance, your load capacitance is in the microfarad range, for example, then this will not affect your circuit, simply because when we have three capacitors connected in parallel, that means that we are seeking for a series or a summation equivalent. So if you are adding something in microfarad with something in a nano or a picofarad, which this will slightly or relatively doesn't affect the overall capacitance of your circuit. But on the other hand, I'm going into CMOS technology. If you remember, we have already talked a lot about the CMOS technology in this course, as well as in other previous courses. And whenever you are target an CMOS or an on-chip capacitance to avoid using the off-chip capacitance and this stuff. In this case, you are going toward the picofarad range or the nanofarad range. Herein, your capacitance or the parasitic capacitance will be in the same range as your load capacitance. And in this case, you will face a problem because your parasitic capacitance will act toward changing your circuit design elements and changing your frequency response and resonance frequency. Herein, you have to have some circuit tricks in order to get rid of this parasitic capacitance, or in other words, to get rid of its effect, because simply the parasitic capacitance is a capacitance that is associated to the MOSFET itself or the BGT. So, in one hand, some design parameters can affect the capacitance. Simply, if you return to the basic semiconductor physics of a capacitor, considering that the capacitance equals to epsilon node, epsilon R, A over D, where epsilon node is the relative permittivity, epsilon R is epsilon node is the permittivity, epsilon R is the relative permittivity. Usually in electronics, we call it K, the electrical constant. A is the area, and over the D, where D is the distance between the two conductors. You can here recognize that once you have a high D, a thick D, the impact of the capacitance will be very small because D is inversely proportional with C. This can be controlled, for example, here, when we consider the C oxide or the oxide capacitance. So having thick oxide layer reduce the value of the C oxide, which is some sort of a added value for your circuits. However, as you definitely know, nowadays we are going toward low dimensional transistors. So when we are going to scale down the dimension of the transistors, we are somehow forced to scale down the dimension of the oxide as well. Another parameter, which is K, the electrical constant of the oxide. So herein, we can act toward having a low K values, a low K oxide. So this is also some sort of a challenge related to the CMOS technology as well. So you can act to decrease the value of the parasitic resistance by, let me say, a fabrication parameters related to the oxide thickness or the oxide electrical constant or whatever. On the other hand, by a way or another, you will still have a parasitic capacitance. How you can redesign your circuit in order to reduce the impact of the parasitic capacitance? This can be seen, for example, in one of these structures, where you are using cascaded configurations. Herein, in a cascaded configuration, as you can see, my dear students, you still have a parasitic capacitance. Connecting here, for example, the base for Q1 to the emitter, to the the collector of the Q1 to the base of Q1, and again collecting the base of the Q1 with the collector of the Q2 with the base of Q2. But as you can see, you are still having capacitance, but you don't have a feedback capacitance. Again, if you remember, a feedback capacitance is the capacitance connecting the output to the input. Here we don't have this capacitance because simply here you are connecting the output to, the input to an intermediate point in the circuit, which is not the output. And here you are connecting the output to the ground, which is a capacitance that can be added here. And you can design your C&L in order to compensate the effect of this capacitance during your design. So you still compensate the parasitic effect or the Miller effect, and you avoid having this feedback resistance connecting the output to the input. Another circuit herein where we have a common collector-based cascaded configuration. So you have this some sort of a mirroring transistors, Q1 and Q2, with the same current source connecting both together. And this mirroring transistor act to mirror the input here. And then you have this RLC filter. Again, the Miller capacitors here are totally disconnected, where still we don't have this input-output feedback in capacitor. So these are some circuit tricks where we can act toward in order to reduce the impact of the Miller capacitance in your tuned amplifier and generally in your circuits. This is all we have for this lecture. Thank you very much for your concentration. And looking forward for a next lecture dealing with another topic with the selected topics in electronics. Thank you very much and see you later on, inshallah.